Okay, click and close real quick. I'll show you something here. We're going to link calculus to kinematics in a way that gives you a whole new different insight on physics. Okay, so let's take an example. How about if we'll get in a little work with trait stuff too. So here's what we got. Attached to we're in the vacuum of space in a spaceship. Attached to this wall, we have we'll make this an oscillator. So we'll have a spring that's attached to a mass, and we've stretched the spring and we're going to let it go. Okay, and it's just going to bong, boing, bong, back and forth, these technical terms. So here's the equation that might describe the motion of this thing. We could say, okay, so something like this. So S of t, S is position, is equal to, we'll just say 2 minus sine t. Okay? Something like that. Yeah, it's pretty simple. Simple harmonic oscillation, and that's a pretty simple form of the equation, but that works. Okay? So we want to answer some questions then. Let's say we want to know some stuff about this. Let's say we want to know the times when the velocity or when the speed is maximum, and we want to know the times when the speed is minimum, when speed is 0. Okay, how can we do that? Okay, everybody's got to close these up now. I insist. This is too good to miss. Too good to miss. Even if you're taking the test, you get back to it, Seth. Yeah, close that up. Okay, so how are we going to find speed? We're going to lean on the physics types a little bit here. Okay, so distance over time. Speed is just the magnitude of velocity. Okay, but now we're moving into a calculus realm a little bit. How is velocity related to position? It's the derivative, right? Okay, so we know that v of t, the velocity, that just means vector, right, for physics guys. Velocity is just s prime of t, which we can do. What does that give us? Negative cosine t, good. And while we're at it, what's acceleration? Good, so it's v prime t or s double prime of t, same thing. And what's that equal to?
Sine t.
Okay. All right, so if we were to superimpose all these then, this is giving us, these are the functions that predict, when, the values of each of these kinematic quantities function at time. Okay? Let's graph them real quick. See something. Okay? Now, we could solve these algebraically, but let's look at it graphically. Okay, so here's my position function. S of t equals 2 minus sine t, and I want to make sure, looks like I'm in radians mode, right? Yeah, it looks pretty good. Yeah, okay. So there's my position function. Does that make sense? If we look at this thing, so we're starting off at the midpoint, and I guess what we did is we gave it a push. We gave it a little ding, and now it's going to, is that right? So, yeah, that's right. We gave it a little push, so it was there, and we just slapped it like that. Now it starts to oscillate back and forth, right? So as time progresses, it gets closer to the wall. The closest it gets is 1 meter from the wall. And then it springs away and gets up to 3 meters away from the wall, and then it goes back to 1, back and forth, right? And if this is a perfect oscillator, there's no decay. It just does this forever, okay? So there's position. Let's graph velocity. I think you can do, let's try something here. I think you can do S prime of t how about that? Okay, that's a graph of negative cosine, isn't it? So do you see what Desmos does? You can graph a derivative. That's pretty cool. Okay, does this make sense? Does this make sense? What's this telling us here? When I smack this thing, you know, I smack it with a hammer to get it going. And what's its initial velocity going to be then? Well, it's -1. It's at its maximum negative velocity, right? And then as it springs back towards the wall, when it gets to its fully compressed point, that's when the velocity should do what? It could be 0 because it's going to bounce back, right? Well, doesn't it do that? Look, as it gets down to its minimum position, the velocity is at 0. Everybody see that? Then it springs back up to its maximum position. When it gets to its maximum position, again, the velocity is 0, right? As it's halfway in between its compressed and stretched position, does it make sense that that's when it's going the fastest is in the middle? Well, look what you see. Where it's halfway in between, it's at the you know, its rest position. So 2 meters is where it's at rest. When it's halfway in between being compressed and stretched, right about there, notice where the velocity is. It's at its maximum. Okay, make sense? How are these curves related mathematically? Well, we know, right? Derivative, the value of the derivative equals the slope of the function, right? So we could also look at this mathematically and say, okay, well, the slope of the function right here is 0, so therefore the value of the derivative must be 0, right? The slope of the position function there is 0, so the value of the derivative must be 0. Agreed? Here's where the function has its largest positive slope, which is 1, and it happens, you know, every cycle it's going to happen, right? Here's where the function, here's an example of where the function has its greatest negative slope, -1, and that also repeats infinitely. Okay? How about acceleration? Let's see if we can take a second derivative. I don't even know. I have a feeling we can, though. Oops. Yeah, it does it. Okay, look at that. Okay, does the acceleration make sense? Let's look at that story. So where is this thing going to be accelerating the most, you suppose? Like if I smack it this way, is it accelerating right there as it goes through the middle? That's the one place where it's not accelerating, right? Think physics-wise. Acceleration is caused by the invisible hand. When it's at its rest position, the spring isn't exerting any force, right? But when it compresses the spring, now where's the invisible hand pushing? If this thing is compressed, we're compressing the spring. You've dealt with springs before. If I compress a spring like this, in which direction is the spring going to push my hand? Back that way, right? So the more compressed the spring is, the larger the force exerted by the invisible hand that's causing the acceleration, right? So where would the acceleration be a maximum then?
When it's compressed.
Good, okay, fully compressed. And then also when it's fully stretched, now the spring's going to be exerting, the invisible hand is pushing the hardest back in that direction. Does that make sense? Okay. So does that make sense in our picture? Let's test it, see if the physics gods know what they're doing. So here's its fully compressed position. What do you know? That's a peak for force. Look at the sign of the force too. They're even smart about the sign. When it's fully compressed, the force is going to be in the positive direction. So the acceleration is positive, right? when it's fully stretched down here, oops, up here, right, when the distance away from the wall is maximum, now the force is equally large, but it's negative because it's pulling the object back towards the wall. How about that? Pretty cool, huh? So where, if we wanted to know where, tell me some points where the speed is at a maximum. Remember, the velocity function is the blue function. So I'll just trace along this, and you tell me when I get to a point where the speed is at a maximum.
Right there.
Okay, there. There, good. It's negative, but remember, speed is just the magnitude, irrespective of sign, right? Just the magnitude of the velocity. So there, there. Every place where we get a peak or a valley on this function, the speed would be at a maximum, right? Yes?
Is the difference between every peak and line?
The distance, well, yeah, it would be, right. It would be. And you'll remember from last year that if we wanted to change the wavelength, we would have to change the argument of the trig function, right? Remember that stuff? Okay. All right. That's it. So now you can do the last assignment. Last assignment is nothing new. It's just, it's a physics calculus assignment.
Awesome.
The last one for this section. So now I'll let you work.